Greetings, math fans. All right, so this is Note Sheet Day 1, basically just an introduction into counting. I'm not really going to read all this because you can just read it yourself. I mean, I can kind of go over it here a little bit, but I want to get actually into some of the problems, okay? So, I can just talk a little bit about here an experiment, difference between an experiment, a sample space, and an event. Experiment is kind of the whole operation where outcome you can't predict it. Okay, tossing a coin, rolling a die. Sample space is the possible outcomes, so like heads or tails, and an event is actually the outcome. Oh, I got a heads. Oh, I got a tails. Okay, and I even say here we're concerned with counting the number of elements in a sample space. The first thing we're going to do here is we're doing a counting tree, and diagrams are very helpful in counting the elements of a sample space. In the diagram, if the diagram is organized and clearly specifies a solution, then it becomes a useful tool in problem solving. A counting tree is such a tool. Okay, so let's just try our first example here. It says count the number of ways 2 coins may be flipped. Well, that's pretty easy. We make our tree here. So this is flip 1. All right, and we could either have heads or tails. All right, and then off this one, or each of these branches, we have heads or tails, heads or tails. This is flip number 2. So really our outcomes are heads, 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 tails, tails, heads, and tails, tails. Okay, those are the 4 possibilities. In fact, that's what we want to do, is we want to figure out how many ways there are, and this way we use our counting tree and we figure out there are 4 ways. Okay, pretty easy. The next one says now construct a counting tree for flipping 3 coins. Okay, so we need to leave a little bit more room here. Again, this is going to be flip number 1, and we either get heads or tails. And then flip number 2, we get heads or tails. And then off of each of these is flip number 3. So it's heads, tails, heads, tails, heads, tails, or heads, tails. Okay? So that means we get heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. Okay, those are the possibilities. And if I count all them up, I have 8 outcomes, or 8 ways. Okay, pretty easy. It says the tree demonstrates a multiplication effect that occurs when action takes place in succession, means right after the other thing, right? Each action has 2 results. In the second stage of the tree, 2 branches stem off the results of the first stage. The third action shows 2 branches coming off of each position of the second stage. Thus there are, and we're going to do a little math here now, there are 2 times 2 times 2. Because 2 possibilities for the first flip, 2 possibilities for the second flip, 2 possibilities for the third flip, and so our total is 8, which is what we got there. All right. This leads to the fundamental principle of counting. If 2 or more actions are performed in a definite order, and the first action can be performed in m ways, the second can be performed in n ways, third p ways, and so forth, the number of possible results of the sequence is the product of these numbers. All right. And it says the fundamental principle can be applied using a method we will call slot method counting. So let me show you some examples here. You toss 3 coins that basically yields 3 slots. And the 2 I put here is basically the number of possible outcomes. So you either get heads or tails. And since there are 3, I'm tossing 3 coins, 2 times 2 times 2, and that's how we get 8 outcomes for the sample space. Okay, example 3, count the number of 3-digit numbers formed from the set of digits 1, 2, 3, 4 with repetition. Now we're going to start talking about that, math fans. We're going to say with repetition. That means I can repeat something. So in other words, if I count the number of 3-digit numbers formed, what I'm going to do is I'm going to put 3 slots. It's a 3-digit number. Okay? And then I'm going to say, well, what can I put in the first slot? I can put either 1, 2, or 3, or 4, right? And again, with repetition, this is actually pretty important right here to recognize that. But it's a 3-digit number, 3 slots, and so the first slot I can put either 1, 2, 3, or 4. You're not going to put the actual number in there. You're going to put the number of outcomes, so the number of possibilities. So in other words, 1, 2, 3, 4, there are 4 numbers. I'll put a 4 here. And then what can go in that next blank? Well, 4, because I can repeat everything. So in other words, I can put the number 1, the number 2, number 3, number 4 in the first blank. I can put 1, 2, 3, 4 in the second blank, or I can put 1, 2, 3, 4 in the third blank. And so that's why you got 4 times 4 times 4, which is 64 outcomes. Now, we're going to do it without repetition. So let's check this out. Okay, the first blank, I can put 1, 2, 3, or 4. The second blank, I can't put 1, 2, 3, or 4 because I use one of the numbers. No repetition, so I only have 3 numbers to put in there. I use one of the numbers again, so I can only put 2 numbers in there. Okay, because I'm using one number. It's without repetition. If I multiply that out, I get 24. Which is interesting. Obviously, when you have repetition, you have a lot more. Okay, almost 3 times as many, right? You have significant more numbers as opposed to this guy right here, just 24. All right. Okay, let's keep going. Some more examples here. Example 4. Count the number of even 2-digit numbers. So we got all kinds of different types of problems here, math fans. Count the number of even 2-digit numbers formed from the set 5, 6, 7, 8, 9. So with repetition. And it even says, important, always assume repeats unless otherwise stated. So we're always going to assume that you can repeat a number. Okay? All right, and it's with repetition here. So, and it's an even 2-digit number, so 2 slots. It's a 2-digit number. Now here's the deal. It's even. What makes it even? Well, of course, if it ends in an even number, so 6 or 8. Do you guys agree with that? So there are 2 possibilities. This is actually the most restrictive spot right here. Most restrictive. Okay? So I use one of those numbers, but it's with repetition. So that means I can go back to the front and I can use how many numbers? I can use either 5, 6, 7, 8, or 9, right? In other words, it doesn't matter. There's nothing taken away. And so that means there are 5 numbers that I can use. And so my answer to this problem is 5 times 2, which is 10. All right? I always write down the most restrictive slots first. Okay, the next one is without repetition. So 2 slots. Again, the most restrictive spot is the 2, or is the last spot because it's an even number. So again, 6 and 8. Now here's the deal. It's without repetition. I use one of those numbers. I mean, let's just write out 5, 6, 7, 8, 9. I use one of the numbers, and it's got to be an even number, so that one's out of there. How many numbers do I have to choose from? I have to choose 4. That's why it's 4 times 2, which is 8. Okay, that's the answer to that one. Okay. Okay, now I just have a bunch more examples here for you. How many ways can a green 6-sided die and a red 6-sided die be rolled? 2 slots. I'm rolling 2 die. Or 2 dice, right? The green is 6-sided and the red is 6-sided. So I have 36 possibilities. And how many ways can a shirt or tie in a shirt be chosen from 3 ties and 5 shirts? Again, it's a slot method. 3 ties, 5 shirts. 15 ways. Okay? A menu lists 3 kinds of soup, 8 main courses, and 4 desserts. How many different dinners are possible if a diner chooses a soup, a main course, and a dessert? Same thing, math fans. Slot method. 3 slots, 3 kinds of soup, 8 main courses, 4 desserts. Okay? And that gives me 96 dinners. How many different dinners are possible if he chooses only a soup and a dessert? So it's 2 slots. A soup, again, there are 3 soups, and dessert, which that means there are 4 of them. So the answer is 12 for this one, 12 dinners or meals. Okay, number 4. Given the set of digits 1, 2, 3, 4, how many different 2-digit numbers are possible? Okay, right? It's pretty easy. If it doesn't say repeats, that means or one or the other, it's definitely repeats. So there are 4 of those and 4 of those, and so we have 16 as our answer. Number 5, given the set of digits 2, 4, 5, 6, find the number of 2-digit numbers where no digit is repeated in the number. Okay, well, It's first of all, there's no restrictions here, right? But it just says no numbers are repeated. So if I start out here, I have 4 possibilities to start out with. I use one of the numbers. I have 3. Now so I have 12 total. The number of 2-digit numbers larger than 50. So 50, it's got to be either a 5 or a 6, right? So there are 2 possibilities. Again, always put your most restrictive spot first. And then since, again, you can repeat, there are 4 numbers. So it's 2 times 4. And so our answer is 8. Okay? Number 6, given the set of digits 0 through 9, find the number of 3-digit numbers possible for the Illinois daily game. So basically what the Illinois daily game is you have 3 barrels, each contain 10 balls, and they're numbered 0 through 9. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. One ball is picked from each barrel in order. Okay? So it's a 3-digit number. So 1, 2, 3. And you can repeat. Okay? It's the way the daily game goes. Because think about it, it's 3 different barrels. So if I pick a 1 out of the first barrel, I can pick a 1 out of the second one, and I can pick a 1 out of the third one. So that means it's 10, 10, and 10. If I multiply those together, I get 1,000. Okay? And think about this, math fans. It's like he's saying 0, 0, 0 to 999. Well, aren't there 1,000 numbers? Because if you go 1 to 999, that's 999, but you have double, or you have triple 0, which is 1 more. So that's why it's 0 to 999. And this is just the pick 4 game, which is 4 blanks. 10, 10, 10, 10. So this is 10,000. Okay? Not bad. Given the set of digits 1, 3, 6, 8, 9, repetition does not occur, so no repeats. Very important. Find the number of 2-digit numbers that can be formed. So draw 2 slots here. Okay? And numbers can't be repeated, so well, we're going to have 5 to start out with, and then if I use one of them, I have 4. So I multiply those together, I get 20. The number of 2-digit or even 2-digit numbers. There's a restriction here. Even 2-digit numbers. Okay, well, look at the numbers. 1, 3, 6, 8, 9. Do you guys agree it can only be 6 and 8? So there's only 2 possibilities. I use one of those numbers because, again, it doesn't repetition does not occur. I use one of the numbers. I only have 4 left, right? So that's why it's 4 times 2, which is 8. And the next one, number of odd 3-digit numbers that can be formed. So odd. So how many numbers? 1, 3, and 9. So 3 possibilities. And then we come to the front, and we can't use all 5 of them. We can only use 4, and then 3, because we use 1 there. So again, my most restrictive spot is that, just like the even one was that. Anyway, my number comes out to be 36. Okay? Number 8, given the set of digits 0, 1, 2, 3, 4, allowing repetition, again, very important. Find the number of 2-digit numbers. Remember, a number can't start with 0. That's important. Okay, the other ones didn't have a 0 here. Now you can't start with 0. So it's 2-digit number. And think about it. First of all, we're allowing repetition. What can you put in the first blank? Anything but a 0. So I can put 1, 2, 3, or 4. So there are 4 possibilities. And what can I put in the second blank? Well, I can put a 0 in there now too, can't I? So 0 is back in the pot, and since it's allowing repetition, I really have 5 numbers now. Because I have 0, 1, 2, 3, 4. As opposed to the first number, I just had 1, 2, 3, 4. No 0. All right? The number of odd 2-digit numbers. Okay, so an odd number, that means it's going to be either 1 or 3. So I put a 2 here. That's my most restrictive spot. And what can I use for the first one? Well, I can use any of them, but I use one of them, one of the odd numbers at the end here. So instead of having 5 to choose from, I have 4 to choose from. And that's why I have 8. Okay, C, the number of 3-digit numbers. So 1, 2, 3. No restrictions here. It can't start with a 0, so it's 1, 2, 3, 4. So there's 4 possibilities. Now I can use any number, right? So it goes back to 5 and 5. And so we have 100. Okay? The number of odd 4-digit numbers. So 1, 2, 3, 4. And they're odd 4-digit numbers. That means this last number has to be odd. So it's 1 or 3. There are 2 possibilities. I come to the front. because, well, actually it's not that bad, but you come to the front, you're allowing repetition, so I can use any number except for 0. So I have 4 possibilities. And then what can I use? I can use 0, so it's 5, and then 5. Okay? And I multiply that out, and I get 200. The number of odd 2-digit numbers is greater than 20. So odd 2-digit numbers greater than 20. Well, first of all, it's odd, so it's got like 2 restrictions here. If it's odd, it can be 1 or 3, so that means 2 possibilities. And if it's greater than 20, it's got to either be 2, 3, or 4, right? 21, 22, 20, or 21, 31, 41. So 2, 3, or 4, so it's 3 there. And then your answer is equal to 6. Okay, the number of 3-digit numbers greater than 300, ending in a 3 or 4. That's a good problem. 3-digit numbers greater than 300, ending in a 3 or 4. If it's got to end in 3 or 4, there's only 2 possibilities. And it's got to be greater than 300, so that means it's got to be 3 or 4, which is 2 possibilities. And what can you put in the middle? Well, can't the middle just be anything? Any one of those 5 numbers? Sure can. So my answer is 20. Okay. Number 9. How many different 6-digit numbers that are multiples of 5 containing only odd digits? So 6-digit numbers, and we're doing, of course, 0 through 9 here now, but 6-digit numbers, 3, 4, 5, 6, that are multiples of 5. What makes it a multiple of 5? If the number ends in a 5 or a 0, right? But it says containing only odd digits. So it can't contain the 0. It's got to actually contain the 5. And that's, I'm just going to put, this is 1 here, right? No, I don't want to put a 5 there. There's only one possibility. It's an odd number, and it's multiples of 5. So it's got to be a 5. And what about the rest of these? Okay, there's repeats, so basically odd digits, there's 1, 3, 5, 7, 9. So there's 5 of them. And 5 of them, and 5, and 5, and 5. So if I multiply 5 times 5, 5, 5, 5, 5, 1, I get 3125. Okay, how many license plates numbers are possible if the license plate numbers are made up of 2 letters followed by 4 digits? So this is, again, repeats possible. So 26 letters in the alphabet, and then 10, 10, 10, and 10. All right, and if you multiply that out, you get 6,760,000. In Morse code, a digit is represented as a sequence of 5 dots or dashes. And how many ways can a digit be represented? Well, here's the deal. It's 5 blanks. It can either be a dash or dot. So there's only 2 possibilities for each of these. Okay, and if I multiply all those together, I get 32. Which makes sense because how many letters do I have? I have 26 letters. So I need to be able to cover my bases, and that's why I have 32 for dashes and dots. Okay, and the last one, Conant Cafeteria has the following specials. Choice of meat, potato, and drink for $1.25. How many different lunches are possible? It's, again, meat is 2. So it's three slots here. Meat is 2. Potatoes, fries or chips, that's 2. And drinks, either Pepsi, 7-Up, or lemonade, that's 3. So you multiply it out, and you get 12. Okay? So that's it, math fans. That's, again, the intro to counting, and hopefully you guys are good to go with this. All right? Adios, math fans. Goodbye.